Hey there, how's it going? So in the previous video, we developed the power rule, which was a rule in the sense of how to differentiate a certain type of function. And what we're going to be doing over the next few videos in this sequence will be to develop some rules which, yes, will apply to the power rule, but more some like generic rules that once we learn how to differentiate some other types of functions, say like logarithmic, exponential, trigonometric, right? Different types of functions that aren't just like polynomials or power functions. These rules will be applicable to any type of derivative, right? So if we're thinking of a constant multiple of a function, something to start with before we even kind of bring in the definition of the derivative is maybe to recall the derivative or the gradient function of just a linear function. So let's say, for example, we had this linear function y equals 7x, so just a straight line passing through the origin. And before we knew the definition of the derivative, how to do the process by first principles, well, we discussed that the derivative is a gradient function. It tells you the gradient at every point on that function. So what's the gradient of every point on this function? Well, it's a constant gradient, so it doesn't matter what the x value is. The derivative is 7, right? The gradient at any x value on the function y equals 7x is 7. Okay, but now that we know the power rule, let's think of 7x as 7 times x to the 1. And also let's think of 7 as 7 times 1. Well, what's the derivative using the power rule of x to the 1? Well, we can bring the power down the front and multiply by the power and subtract 1 from the power. Right, so going from here to here, right, we've brought the power down and subtracted 1 from the power. X to the 0 is 1. 1 times 1 is 1. Right, so you can see that here, if we think of just what a derivative is, we get the derivative 7. And then if we use the power rule, ignoring the 7 for the time being, right, we use the power rule that we now know, just on x to the power of 1, we get 1, and the derivative of 7x is 7 times the derivative of x. Okay, so that might give us a bit of a clue as to how to do this. All right, maybe by chance it just works for linear functions, but in fact it will work for any functions that, any type of function that if you have, if you know how to differentiate a certain function and you've just got a constant multiplying it out the front, the derivative of this function will be the constant times whatever the derivative of that function there happens to be. All right. So let's just try doing this with another function, just to get a feel for it. And see if this ends up working with another function, you know, because we can't just reason from looking at this and saying, oh, the derivative is blah, right? Because here we could reason from here what the derivative was, because it was a linear function specifically. But here, let's say we have y equals 5x squared, we're going to have to use the definition, all right, to differentiate this. So the derivative is going to be the limit as h goes to 0 of, and we're going to put x plus h into the function. We're going to minus the original function, and that's all going to be over h. All right. Now, without kind of doing the rest of the steps, we could expand out this perfect square, right? And we get, you know, x squared plus 2xh plus h squared, all of that times 5. and then we'd have a 5x squared minus 5x squared, cancel out, blah, 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 blah. But what I want to do here is notice that both of these terms in the numerator have a common factor of 5. So we can take that out, and I might even write that over h there. Right, so this is 5 times that minus 5 times that. Now, the property of limits is that we can't, if we've got anything with containing an h in it, we can't bring that out the front of the limit, right? We can't extract that some factor outside the limit. But if it's a constant number, or even if it's a pronumeral that we're not taking the limit with respect to, we can bring that constant out. So we can bring this 5, this limit of h goes to 0 is 5 times blah is going to be the same as 5 times the limit as h goes to 0 of blah. Okay, and then we know from when we've done this previously that the limit of h goes to 0 of x plus h all squared minus x squared on h. If we were to do the algebra, expand out the perfect square, cancel out some like terms in the numerator, factorize out h, divide through the common factor of h in the fraction, we would in fact get, right, well, this bit here is now also using the power rule, derivative of x squared, bring the power down to x. Okay, so you can see for that specific function that the derivative of 5x squared was 5 times whatever the derivative of x squared was, which from the power rule we also know is 2x, as well as we've already evaluated that expression before. Okay, so I'm going to rub a few things out here. What if instead of 5 times x squared, I just had some number k, and then instead of specifically having x squared, maybe I had x cubed or x to the 50, or who knows, some other function, right? Like e to the x or cos x, right? So if we had k times some function, okay, what would the difference be in the working out? Well, everywhere we had our constant number 5, well, rather than 5, we could have 5 or 7 or 10 or -3, right? We could have some number k, and all the exact same logic that we did with that 5, we could do with, whoops, I was about to rewrite 5. Right? All that manipulation we just did with that number 5. 5 wasn't very special. We could do that with k, you know, whatever number that happened to be. And then just everywhere we specifically talked about the x squared function, we could have just been talking about any other function, right? Right, so if we just to start off, and hopefully the rest will become obvious, filling in the gaps, k times, you know, like 5 times x squared, just applying the definition of the derivative, we have putting x plus h into the function, so k times f of x plus h, minus the original function k f of x, right? And then the rest is kind of going to all fall out with the structure there in place that we had specifically for x squared, but we could talk about any other function as well, right? So we could take out that common factor of k like we did with 5, and then once we had our factor 5 or k, we can take that outside the limit. And then since we have k times limit as h goes to 0 of f of x plus h minus f of x all over h, we have k times, well, this expression here is just the definition for the derivative of this function here, right? So just to summarize that maybe in one go, we have, if we have y equals some constant times a function, this is going to differentiate to whatever that constant is multiplied by whatever the derivative of that function happens to be, which at the moment we only know as how to do with the power rule, but again, like I said, once we've established a few more rules, then we'll start to look at some other types of functions. All right, so just a few examples of how to use this. All right, let's just pick some new number. Let's say we had -8 times x cubed. Well, -8 is a constant, so the derivative of -8 times x cubed is going to be -8 times whatever the derivative of x cubed is. And x cubed, we can use the power rule, bring the power down and multiply by it, and subtract 1 from the power. And then of course we can simplify -8 times 3 is -24x squared. Alright, another one. Remember, we sometimes will use the power rule with not just straightforward, like, you know, some nice positive integers, but we could have negatives and fractional powers as well, which we might have to extract out of an equation before we actually apply the power rule. So let's say we had y equals 6 on x squared. Well, this doesn't immediately look like a constant multiplied by a function, but of course 6 over x squared is the same as 6 times 1 on x squared, and then 1 on x squared we can now bring that up with a negative, change it from the denominator into the numerator, changing from a positive to a negative power. Okay, so now we have a constant number times a function which we know how to differentiate. So we're going to use the fact, this new rule, that the derivative is going to be this constant number times by the derivative of x to the -2, which we can again use the power rule for. So bring the power down the front and subtract 1 from the power. And then we can tidy this up. We're going to have 6 times -2 will be -12, and then x to the -3, we can do the reverse of this and then bring the power back into the denominator as a positive power. There we go. Alrighty, one more with a fraction maybe, or something that's going to end up as a fraction. Okay, let's say we have y equals root 3x. So here we know that square root of 3 times x, we can split that up into root 3 times root x. Alright, and then root x we can represent as x to the half. Okay, so now we've got this, we've changed this expression, so we've got a constant multiple times by a power function, right? So we can differentiate y equals root 3x, which is equivalent to root 3 times x to the half, by multiplying this constant, root 3, by whatever the derivative of x to the half is, which is, bring the power down, half, subtract 1 from the power, right, and then we're going to have root 3 over 2 and just like when you do x to the negative half, with or without the root 3 constant out the front, negative is going to become x to the positive half down in the denominator, and then just like we change root x to x to the half, x to the half, positive half is going to change back to root x. Alrighty, so there we have the constant multiple of a function. If we differentiate it, is just that constant multiple multiplied by whatever the derivative of that function happens to be. So like I said, this rule, while we've only seen it kind of interact with the power rule, this you've noticed I've written quite generically, just with any old function. So this rule will be applicable once we end up covering the derivative of other types of functions. But that'll come in a later video, and that's it for this one. So catch you later.